This video looks at correlation. In quantitative research, you measure variables to see if group differences in the independent variable are reflected in the measurements of the dependent variable by comparing the means of each. The other way is looking for a relationship among variables, measured on a continuous range of values. This relationship is called a correlation. Strictly speaking, correlations require that at least two variables are measured at the interval or ratio level. It's a mistake to refer to a group variable like gender and say gender is correlated with amount of speaking, because Pearson's R defines correlation as a relationship among variables, not a difference among groups. Spearman's rho uses rank-ordered data, but I recommend you simply avoid ordinal-level data and use Pearson's R instead. Many of you already know that correlation is not the same as causation, because the two variables are rarely time-ordered, just a snapshot. Still, we generally interpret common-sense relationships. For example, we know people who smoke are the same people who risk disease, so we assume the smoking is causing the disease rather than the disease causing the amount of smoking. But in the absence of a controlled experiment, it's wise to remember that in less common-sense examples, we don't know which variable came first. When we read that people who are depressed also spend a lot of time on social media, it's not clear which variable caused the other. Pearson's R is a coefficient that ranges from 0 to 1 when two variables are in a direct relationship, that is, positively related. The coefficient ranges from 0 to -1 when the variables are in an inverse relationship, that is, negatively related. If relationships are curved, sometimes positive, sometimes negative, then they form a curvilinear relationship. Without a scatter plot, the value of Pearson's R for a curvilinear relationship may approach 0 and be mistaken for no relationship. Pearson's R indicates only the magnitude of the relationship, and then the negative sign or its absence tells you the direction of the relationship. The magnitude of Pearson's R is deceptive until you square the value, that is, R squared, to estimate the coefficient of determination. Loosely speaking, a correlation of 0.50 between two variables allows the researcher to expect that the variation in one variable accounts for 25%, that is, 0.50 squared, of the variability in the second variable. Scholars disagree on how much determination actually takes place, but R squared is called the coefficient of determination. Let's look how easy it is to calculate Pearson's R using SPSS. You may have used the manual calculation in a statistics course, but SPSS is faster. I've entered some textbook data using interval level, time of day, and ratio level, number of news stories, taken from September 11th, 2001, to see if time of day affected the number of stories. You'll see at 9:30, shortly after the Twin Towers came down, there were quite a few stories. The pattern for the rest of the day is worth observing. To calculate Pearson's R, you click on Analyze, Correlate, Bivariate, and the variables to choose from are always on the left-hand side. I've worked ahead here, so I've already moved time and stories to the right-hand box. The right-hand box is where you put the variables you're working on in a correlation. Pearson's is already checked when you fire up SPSS. Everything else is all set. All you have to do is click on OK. You'll see that the value for correlations is -0.39, rounding to the nearest hundredths. The significance of the statistic, that is Pearson's R, is usually labeled P, but in SPSS it's called sig or significance. The test for statistics is P must be less than 0.05. We only have 24 cases, so even though the correlation seems to be moderate sized, the number of cases makes it not quite significant. The values shown in this table don't tell you everything. It's a good idea to use a scatter plot to examine for outliers or curvilinear relationships. To do that, you go to the Graphs menu, Legacy Dialogues, and then Scatter Plot, or Scatter Dot in this case. You'll next see a little box that you can choose Simple Scatter and then Define. Stories is already on the y-axis. It's our dependent variable, which is typically placed on the y-axis. And our predicting variable, time, is, as usual, put on the x-axis. Click on OK, and you can see your graph. Using the chart editor, I fixed the times at the bottom to read 8 a.m. all the way over to 9 p.m. to match the table. The next step is to fit a line that best approximates the data. You do that by double-clicking on the graph, which brings up the chart editor. Under the Elements menu, there's a selection called Fit Line at Total. It defaults to a linear graph. You'll notice it says linear in the properties box. You'll also notice that this is the best fit in a linear model, which says R squared is 0.04, or only 4% of the variability in time of day is associated with the variability in the number of stories. 4% is not very good. Perhaps the data are curvilinear. If you click on quadratic and hit apply, it plots a curvilinear line. R squared now is 19%, or 0.19. 19% is a better prediction. And if you kind of look at the dots, they look like there's not that many stories in the morning, more in the midday, and then fewer at night. Ordinarily, the next step would be to look for outliers, but we're running long. I'll do another video specifically about outliers. Until then, see you next time.